I'm BarryBarish. I'm a physicist. I was educated in Berkeley and have been at Caltech my whole career. And I'm going to talk today about gravity. Okay? We all know about gravity. So gravity is basically something we experience even as a young kid. It's one of the fundamental forces in nature. We have different forces in nature, one that has to do with electricity, one that has to do with gravity, one that has to do with what holds us together, one that has to do with what makes us fall apart. And the one that probably most of us experience at the youngest age, and the one that I'll give you a little talk about where we've learned something new about gravity, is gravity itself. So this story begins, of course, in ancient times, because people have always experienced gravity. We can't jump off the earth. We just basically are stuck here. The first really important understanding of gravity came from Sir Isaac Newton. So Sir Isaac Newton, who was one of the great scientists, probably the greatest physicist, arguably, and historically, wrote his masterpiece called the Principia in, I think, 1687. He rewrote it over many years, but I think something like 1687. And in it, he describes his theory of gravity. It's not all his, but it's his theory of gravity. And in fact, he calls it unified gravity. So what I'm going to talk about first is unified gravity. Why do I emphasize the word unified? It's because you write down one theory and it applies to everywhere where gravity is used. So the idea that he has done this came from the fact that gravity was experienced in many, many different ways. I mean, classically, we think of it as the apple falling onto the tree. Secondly, we know that something makes the moon go around and not escape from its trajectory around the Earth, or the Earth around the sun. Later, we learned that gravity also affects things like the tides, that the moon goes over and affects the shape of the Earth, and so forth and so on. So gravity has many, many effects, and Newton told us that there was one formula that described the force, and it had a constant, had whatever the bodies are that are feeling the gravity over r squared. This is the famous formula. So what it implies is that if I have two masses, that the force between it will be inversely proportional to how far apart they are, squared. The product of the mass of this one, I'll make one bigger than the other, and this one, and a constant here. And this described everything, presumably, from the apple falling out of the tree until we described something more subtle like the tides. And arguably that formula, that theory, if you call it a theory, is maybe the most successful theory in the history of physics. Lasted over 200 years. It described many practical things, and that was done by Newton. So, fine, he gave this. By the way, it wasn't a complete theory, because that's the way physics works. He didn't know what this was. It's a constant. But he said it's a constant. It's not something that changes like this changes. It's just there. It's a constant. But he wasn't able to tell us how strong that constant was. And it took 100 years for that constant to be determined. That constant was finally determined by using a particular method called the torsion balance. And a torsion balance is a rod and then horizontal, two masses, and you twist it, and it tries to come back to itself. And so he made a torsion balance. You twist it, it comes back to itself. He measured how much force it took to do that, and then brought up 2 lead balls and measured that this, was able to measure what this was. That took 100 years. And interestingly, the first measurement of this is consistent with the best measurements done today, several hundred years after that. So this is the basic theory of gravity. It doesn't explain, and this is the way physics works, it doesn't explain, as successful as it is, it doesn't explain some fundamental issues with gravity. The first one is that when the apple falls from the tree, we as an observer see that instantly. So this theory has instantaneous action at a distance. And that's a problem. Our limitation in the theory. Because if we have instantaneous action at a distance, it's easy to see that that's impossible in certain physical situations. The way I like to see it quickly is that it takes a fair length of time, 8 minutes, for us to know or for us to detect anything that happens at the sun. So a flare goes off, we know about it 8 minutes later. If the sun were to disappear right now, we wouldn't know it for 8 minutes. But the gravitational signal then can't come immediately. And so this was a problem that exists in Newton's theory as successful as it is as a theory. It really wasn't able to describe that. Secondly, as good as this formula is in describing everything, it has a problem. And that is, it doesn't tell you why. What I mean by why is, why does the Earth pull you down? I give you a formula that it pulls you down, but what is it about the Earth or the object on it, the apple, that makes it attract to the Earth? So why does gravity work? I prefer the old slate chalkboards, to be honest. So the Earth pulls you down, and these were the 2 fundamental questions. So as successful as the theory was, it's not complete. And that's the way theories work in physics. That there's nothing now that I'm going to talk about replacing this theory. That doesn't make this theory wrong. In physics, when we have a development, maybe there was something wrong, but in general, we're more refined. We have to develop something that maybe is quite different. In this case, what I'll talk about is quite different, and it fixes these problems here. But that's not to say anything about this, because in the limit of doing what we describe with Newton's theory, it's the same. So these theories are really the same for most of what we do in nature, and then things get more refined. So this is Newton, and then 200 years later, Einstein came along, a little more than 200 years later. And when Einstein came along, other than these, which are conceptual problems, there was only one small issue with Newton's theory of gravity. And that was the observation that the orbit of Mercury around the sun, so we have the sun, is very elliptical and comes back to a slightly different place each time around. And the distance between these two, you should be able to calculate from all the known gravitational sources, the planets and so forth, that are around the sun. And the answer was about 10% wrong. So Newton's answer for this one physical phenomenon was wrong. It was the only thing detected as being wrong. From the time when Newton existed, of course, we didn't know as much about the solar system as we do now. So most of the explanations that people had were that we were missing, this is Mercury, some matter, maybe a planet, that existed between Mercury and the sun. That was proposed as a solution in about 1840 or 1850, long before Einstein. There were various claimed observations of objects between Mercury and the sun before Einstein came, between 1850 and 1900. They were proven to be wrong. So by the time Einstein came, this theory existed with these conceptual problems only, and the only observation in nature that existed otherwise, only observational problem with Newton's theory is this. Many people, when they describe why Einstein developed the theory of general relativity, point to this. I personally think that that's not what happened at all. As physicists, we celebrate Einstein because he solved several of the most important fundamental problems we had in physics in the year 1905. That's when he came on the scene. And in the physics community, there were big celebrations in 2005, the 100th anniversary of Einstein's great year, where he solved several problems for us. Interestingly, he could do these one a month, more or less, over a period of time. And then it took him 10 years to develop the next theory of gravity. So the motivation, in my mind, had to come from more than a slight deviation in Newton's theory, and in fact, one that maybe we still hadn't done a good enough experiment. And in fact, NASA did a rather ambitious set of observations when they were able to look for matter between Mercury and the sun, and they didn't find anything, and were able to put a limit, I don't remember exactly, of something like nothing. There was nothing as large as 10 kilometers in size. I may not have the number right, but something like that. So Einstein came along, and basically he wanted to solve these two problems, and he had already introduced to us what's called the special theory of relativity. That's what happens when something goes at high velocities, near the speed of light. And the obvious next thing theoretically to do is add acceleration to the problem. Instead of just high velocity, add acceleration. And that's fundamentally adding gravity. Gravity is acceleration. So Einstein added acceleration to the special theory of relativity, his famous E equals. So we had the special theory of relativity, he added acceleration. He had a lot of trouble doing that because the mathematics became extremely difficult in the way he did it. And he had to learn mathematics and get help from mathematicians, and finally came out with a theory that immediately he had to modify because he had made some mistakes in 1915. So in 1915, and this was, I don't know exactly, but I think 1687. maybe 7. Einstein then, over 200 years later, made his new theory called the general theory of relativity. And the general theory of relativity then solved these problems. So it solved these. That's good. It also plus predicted bending of light. And that was seen in 1919. From the bending of light that came from stars going behind the sun at the same time there was a solar eclipse. This basically said that general relativity was a viable theory. There was one other prediction that came out of the theory. And the second prediction, so this is prediction number 1. The second prediction was the existence of gravitational waves. This came about because of the fact that you can set up the equations of general relativity in a way that looks very much like the equations of electricity and magnetism. Electricity and magnetism has waves. And so being Einstein, he didn't derive that there would be gravitational waves from general relativity, but rather made the intuitive leap that if the equations look so much like the equations of electricity and magnetism, there must also be waves in general relativity. So he predicted the existence of gravitational waves in 1916. And there's a long history between where people tried to see if they could actually derive gravitational waves from the theory of general relativity. That wasn't done until the 1950s. So it took 40 years almost to do that. In the 1950s, at the time that was done, it was also evident what the observational effects of general relativity might be. And that inspired doing experimental work. So the search for gravitational waves began in the 1960s. And a different technique from what we use now was done first. All searches failed until we managed to come along. And so then LIGO began construction. I emphasize the word construction because we did a lot of work on the ideas of how you'd make a detector to detect gravitational waves before this, but we began construction in 1994 and observed gravitational waves in 2016, essentially 100 years after Einstein had predicted them. So it took 100 years to actually detect gravitational waves in the year 2016. That basically showed that Einstein's theory of general relativity was right. We also knew that it was right at the level that you can do this. We don't know yet that it's the final theory of gravity. There are alternate theories of gravity that are consistent with what we've done so far. So one of our challenges for the future is to understand whether there's a further evolution past Einstein's theory of general relativity. And so since we detected gravitational waves, we're looking in detail at how consistent they are with Einstein's theory and with alternate theories. And so one of the big goals of the future, just like we moved in the future here, is to understand whether the true theory of gravity, or the theory of gravity that best describes nature, is Einstein's theory or a variant, and there are variants that are proposed. Lastly, we now have a different way to look at the sky. So as humans on the Earth, we look out and have learned a lot about, this is astronomy. We've learned a lot about what's out there, from stars, now even planets and other star-like planets in other galaxies. We have been able to see back enough to draw a model, which may be right or may be not, of how the universe evolved in the first instance itself, how long it's been around, all kinds of things through astronomy. But astronomy has been all through one form or another electromagnetic radiation. Electromagnetic radiation being photons, which we observe through a telescope, or different wavelengths of photons. We're, for the first time now, more or less in the situation that Galileo was in 1607. And in 1607, Galileo, for the first time, used a telescope. He didn't invent telescopes. The telescope was actually a product of the fact that lenses had been made for glasses at that time, and some people had made the first telescopes out of that just to magnify. Galileo, for the first time, actually took the fact that we had a new instrument other than our eyes to look at the sky, and that's a telescope, and he saw, and he looked at Jupiter in that year and saw that it had 4 moons. And that was the birth of modern astronomy, because that's the first time that we learned about astronomy from something other than just our naked eyes, looking through an instrument and seeing that the Jupiter had 4 moons. Now we know there's more than 4 even, but saw 4 moons. From that time, we've had 400 years of the development of astronomy. Now, for the first time, we have astronomy with gravitational waves. And that's our future. That is, looking at the sky, much in the same spirit as astronomers have done, but looking at phenomenon, objects that give signals that come from gravity instead of electromagnetic radiation. And those can be other physical phenomenon from the same source, or it could be something that's quite different than that. And so far, we've seen something that astronomers have very much difficulty seeing, only inferring, and that is black holes. And also, we've seen a second kind of event that has to do with what we call neutron stars. But in general, I think this is the birth, very much in the spirit of Galileo in 1607, and we have no idea, but I believe that 400 years from now, it's been 400 years since Galileo, that we'll know a lot new about the sky through using this new tool that is gravitational waves. And I filled up the blackboard, so I'm done. What's the date?
11/12.